Hello, how are you? Good afternoon. We are ready to start with this seminar. So it is my pleasure to introduce Professor Onur Bilgen. He will be talking about some of his exciting research in the area of drones. So many things happening in drones, so many new things. It's a transformative technology that is going to change many of the way we do things. So what better to have an expert in the area that is doing fundamental research to advance how these new devices will operate and all the interesting and complementary activities that this new technology is affording us to do. So Onur did all his mechanical engineering degrees from BS to the PhD at Virginia Tech. Then he was a postdoc at Swansea in UK. He was recruited to Old Dominion, and we were very excited and very lucky that we were able to recruit him into our School of Engineering in 2017. And he has set up his lab now in our new building at Richard Weeks Hall. And he will be sharing some of the activities and research that he's been doing in that regard. Of course, I mean, he has developed a very evolving and nice program. He received a very nice award from ARPA last year, very large project related to how to operate with wind and all energy devices. So, but without further ado, let me share the floor with Onur. The talk for today is drones that are quiet and flight like birds, using smart materials to create a new generation of air vehicles. So before we start with the presentation, a couple of administrative things. One is that I'm recording this meeting, so we will make them available later on through the school website. So in addition to that, we will have a Q&A at the end. So if you forward me your questions through the chat, I will make those questions to Onur. I will probably combine some of the questions, and but we will answer all of them. So without further ado, Onur, the floor is yours. I will mute myself and stop my video, and there we go. So for all the attendees, if you send me a chat message, I will be able to see it. And please send me questions at any time. I will be compiling them, and we will leave it for at the end discussion. Thank you. Onur?
Okay, Professor Coutinho, thank you very much. Can you hear my voice clearly?
Yes, I can.
Okay, very good. And you can see the screen and my mouse?
Yes, I can.
Very good. Okay, let's begin. So let me just pull this laser pointer. Okay, so you should be able to see a laser pointer now. All right. Well, good afternoon, good evening, good morning, wherever you're joining from. Well, it's certainly afternoon or afternoon here, and it's a nice and rainy day. So thank you for coming to this talk. My name is Onur Bilgen. I'm a faculty at the Mechanical and Aerospace Engineering Department. So today I will be giving two presentations for the price of one, so to speak. So the first presentation is actually from a proposal that we submitted to the Rutgers Big Ideas Symposium last year. This event was organized to collect ideas for the upcoming capital campaign for Rutgers. So in this first presentation, I will show you the big picture regarding drones and kind of to give you an overall idea of what the technology might become in the future. So the second presentation will focus on my research and will be a little bit more technical. So let's get started. Okay, so the average American spends about 54 hours sitting in traffic every year. And it's 83 hours actually for per year for those in the 15 largest cities in the US. So if you're from the New York City metro area, 83 hours is average the amount of time that you spend in traffic. So the total economic loss due to wasted fuel, which is about 120 gallons sorry, 320 million gallons of fuel alone adds up to 15 billion for the New York City metropolitan area, and a total of 165 billion in the U.S. annually. Okay, so this unimaginable amount of waste is due to current limitations in ground-based transportation and distribution systems. As you very well know, many urban roads and public transportation routes are already over their capacity, and we simply cannot build more. So we urgently need a more sustainable way to transport goods, people, and we believe that the solution is not in the air, sorry, not in the ground, but in the air. So you see this image. This is actually the cover of one of the covers of Time magazine. It's actually built by hundreds of drones to generate a frame in air at nighttime to frame for the magazine, and also write the letters TIME, spelling out time, also using drones. Okay, so they've done this with collaboration of one of the Intel drones, and it really says it all. I think we're at the beginning of the so-called drone age. And this is a moment in history that is similar to the arrival of the iPhone in 2007. And just as, so the iPhone and the smartphones since then became a platform for innovation rather than just to make phone calls. We believe that the drones offer the same kind of platform for innovation, not in your pocket, but in air. Drones are definitely a key technology for aerial automation, robotics, rapid distribution of goods, food, and medicine. And just like smartphones, Facebook, Twitter, Google, drones are here to stay. And drone technology is already being applied in many positive ways. So here's an example. So many companies are already using drones to make work safer for their employees. This is a very large cable stabilized tower. And instead of climbing or instead of using a helicopter with employees, the company is using drones to inspect this tower and the cables and the structural integrity of the system. Scientists are using drones to track and help endangered species, as you see the whales in this example. And drones are already helping save lives by delivering medical supplies in Rwanda, Tanzania, and other countries. And you would have heard recent news that Amazon and other companies have been doing this in the United States. Okay, so here's a large fixed-wing drone, not a multi-rotor vehicle, but a fixed-wing drone. And here's actually a launch mechanism. These vehicles are able to deliver medical supplies, blood, for example, within 15 minutes instead of 3-4 hours by ground. And this is one of my favorite applications. Drones help shoot incredible action scenes. So this is actually the high-speed motorcycle chase scene in Istanbul from a James Bond movie. And of course, there are many more applications for drones. There's just too many to list here. So despite all of these current uses of drones, there's still many significant obstacles to realize their societal impact that we foresee. I'll focus on a few on technology and airspace related issues. So for example, in terms of technology, the current drones cannot navigate through even the simplest obstacles. They're fundamentally speaking, they're inefficient, noisy, and they have very little autonomy. So a recent NASA-sponsored survey for public acceptance indicated that people are concerned about the noise and visual disruption, as well as safety and privacy concerns. Okay, and in fact, noise is one of the biggest problems in the drone technology today. So there are, of course, other issues related to policy. So the National Airspace System, or NAS for short, has very limited data on drones and their interaction with humans and other aircraft. And we simply don't know all of the challenges presented by drones, particularly in urban environments. This map shows the areas currently restricted by the FAA for drones. So both DC and NYC are pretty much no-fly zones. This means that today we're either fully or partially restricted to operate drones in these areas where we need them most, particularly in these urban areas like New York City and DC. So to move forward, we need facilities to design, manufacture, and test drones. We also need to be able to control air traffic due to operation of these drones. And we recognize that there no such place currently exists. So we proposed a solution. We believe that the airspace and technology issues will be solved in the next 2 decades by research and development. But the solution is really to enable that research and development and to enable operation of vehicles developed with that research. So to this end, we propose to establish what we call a drone port. Okay, this would be the world's first center for aerial automation. So in the long run, a drone port should look at least, or function at least as an airport-like facility with an ability to serve a large number of air vehicles and passengers. And a drone port could essentially be located in an urban area. So, for example, like the Penn Station for trains or the Port Authority for buses in New York City. And in this image, this artist's rendering, we're showing a bespoke design of a future drone port vision located in Manhattan to show how a drone port might look like in the future. And you might recognize some of these geographic features. This is the Hudson River. So we're on the west of Manhattan. This is the Javits Center. This is the new Hudson Yards. This is actually where the trains actually park. So if you go onto Google, you'll be able to see where this is. And we thought that we will just drop our drone port right here, because why not, right? So to reach this future vision, a drone port must also include critical research and development facilities. It must be a place where academia, industry, and government can collaborate. It should enable the development of medium-sized air vehicles for personal transport. In addition, small drones should be designed and developed for many applications that may become profitable as early as 2028. And these applications would include food transportation, medicine, first aid delivery, emergency Wi-Fi service, and for agricultural automation, environmental monitoring, so on and so forth. So it's clear, right, that a drone port in Manhattan is not yet feasible. And we also know that such facility cannot be possible without institutional capacity and also doing this or starting this in a right location. So we thought that we could do this in Rutgers or near the New Brunswick campus. So this is a map of the campus in New Brunswick. And a drone port on or near the campus would allow us to have locally controlled airspace. And in fact, we don't have any restrictions within this airspace that is shown here. So one of the advantages of being in this area is that, in fact, we're located in the busiest metropolitan corridor in the United States. We have our location has access to New York City, Philadelphia, DC, Boston. The area supports a 1.6 trillion gross product economy, and this is pretty much larger than all but a handful of economies around the world. And New York and New Jersey are home to the nation's most extensive public transportation network and two of the largest container ports on the East Coast. It's also the busiest location for supply chain activities in the nation. So we thought that there's simply no better place to build a drone port. Okay. So from 2025 in the short term to 2050, the drone port at Rutgers will primarily serve for research and development. And as research ramps down, the passenger transportation would ramp up, and which would, along with the regulations and technology. So in the future, the Rutgers drone port will actually become part of a network of ports all around the world. So this is just potential airways to different cities, and of course, urban transportation within the cities. So there could be flights across the nation, and all of these drones would be modeled after the road. All of these so-called drone ports could be modeled after the Rutgers drone ports, which would have been the first one of its kind. And so who knows? I mean, maybe either my vision or somebody else's vision of a drone port will actually become a reality in the future. So this is kind of a summary of the proposals that we made. I don't know if we want to take questions, take a little break for questions regarding this kind of a introductory presentation, or if there are no questions in the chat box, I can continue.
I would go all the way, and then we will allocate some time for the chat. I mean, for the Q&A during the chat. Okay?
Okay, sounds good. Okay, so let me switch then into the second presentation. Okay. Okay, so welcome back again. So this is my second presentation, which will focus more on my research. Again, my name is Onur. I'm a faculty at the Rutgers Mechanical Engineering Department. So the title or the discussion today will be on my research on drones that are quiet and that fly like birds. And the way that I've been doing this is to use smart materials to generate new systems. And I'll talk about what I mean by smart materials. Okay. So my main goal has been to use or propose, model, test mechanically simple designs to solve common engineering problems. So what do we mean by smart materials? Smart materials can be materials that change their shape due to external stimulus that is beyond what so-called conventional materials do. So we know that many materials, especially metals, they change their shape or they expand and contract because of temperature. However, this effect is very minor and it's not very useful in most cases. However, when we talk about smart materials, we can actually have materials, metals or alloys, metal alloys, that can actually change their shape significantly with the change of temperature. We can change certain materials, change their shape because of applied electricity. That would be called a piezoelectric material. Some materials have the ability to heal themselves after they have been broken or separated or cracked. These are self-healing materials, and these would also be considered as smart materials. So when we use, instead of taking common materials or traditional materials and assemble them in complex fashion to get functionality, if we can actually build function within the material and use the material itself by itself without combining with other systems or other materials, then we can make much more efficient and lighter structures and much more intelligent and clever structures and systems. So, but at the end of the day, when we use smart materials, we may be able to, of course, reduce power consumption, allow for compact packaging, reduce fabrication and maintenance costs, and overall we can increase functionality by using the same material to actuate, sense, or even harvest energy. So this is kind of the motivation or the driving point of my research. So I don't want to go into too much of the technical details. I'll just talk about a few things. So the material that I'm going to be showing today is a piezoelectric material. It's a type of a smart material. Basically, what it does is that when you apply force to it, it produces electricity or charge. In return, also, if you apply electricity or charge to it, then you will get motion. So this so-called indirect effect, the piezoelectric effect, is what I'm going to use to apply electricity to the material to change its shape, and this shape change will be used to change shape of aerodynamic structures. And we do this in a very based on a very simple mechanism. So let's just look at this one here. So we have an active material or a piezoelectric material. I will apply voltage to it. And when this material at the top surface expands, it actually moves the passive material attached to it. And because there's an offset of this expansion force at the top level, the overall motion is that a change in curvature. So this plate expands in the horizontal direction, whereas the overall structure changes its curvature. So this is the underlying mechanism that we're going to use to generate large shape deformation using very small amount of motion. Okay? So here's the outline of my presentation. We'll first look at smart materials and their application on small aircraft. This is kind of the beginning of my research. Then a few years later, I moved on to airfoils. Then I worked on a solid-state ornithopter, which is more bird-like a drone. And then recently, I've been working on applying a similar technology, this kind of a compliant or bird-like, wing-like technology onto rotors. So let's just we're going in chronological order here. So demonstration on small aircraft. So when we first began this research, there were very few examples. In fact, there were no examples of what we exactly did, or we did. So this actually in 2007, 2006, 2007, when I was a student at Virginia Tech, I developed this, I modeled, simulated, and then fabricated and then tested this aircraft, which has these piezoelectric materials. So these orange patches here are patches that deform the surface. So when you apply electricity to it, this wing actually changes its curvature. It starts increasing, it cups or it basically curls as the electricity is applied. So normally there would be motors and actuators, maybe 10, 15, 20 different parts to achieve the same thing. With this design, we achieved the change in shape of the wing with only technically two parts, the active material and the passive substrate here. So at one of the conferences, AIAA SDM conference, this research received the best paper award for the entire conference. So that was one of the starting points for us. I then went on to advising or co-advising a senior design project with my advisor at the time. So based on that aircraft that I showed you earlier, which was my master's thesis actually. So during PhD, I worked on this. So we, with the senior design students, we actually implemented the same idea on the main wings and on the tail as well. I developed custom electronics for it, and we implemented it, and then we flew this aircraft. So now the first aircraft became the first direct or solid state piezoelectric controlled vehicle for roll motion, the lateral motion. And this aircraft became the fully solid state controlled aircraft, where both the main wings and the tail was also controlled with smart materials directly, without any linkages or mechanisms. So one of the things that we had to solve in this project was just electronics, small electronics. So these actuators use high voltages, and at the time there were no compact electronics to get from low voltage battery voltage up to high voltages. So this is one of the challenges that we solved. And then this actually research or senior design project became part of a PBS Nova Making Stuff series hosted by David Pogue. So it was part of the Making Stuff Smarter because the materials that we're using are smart materials. So you can look at these videos, and I'll actually show a link later on at the end of the presentation, and you can actually look at these videos on your own if you like. So that research, that early research led to some commercial impact. The Smart Material Corporation developed these compact amplifiers. And also another company developed this System Dynamics Inc. developed an aircraft based on this idea. So in fact, you see that this aircraft looks just like a bird, except that it still has a propeller. So to remove the propeller, so to have the wings not only create lift, but also create lift and thrust is actually a big challenge. So this is actually one of the projects that I'm working on now. Right. Next thing that I worked on are the piezo composite airfoils. So I'll just talk about modeling and optimization very quickly. So we, in every step of my research, I try to take things or do the research process from A to Z as much as possible. So I start with conceptual design and then some detailed design and then modeling and then simulation and then optimization and then testing certain specimens and validating them. So this is one of the concepts that we come up with to address some of the drawbacks of the previous designs. We thought about where we can put the piezoelectric materials, how we can hold this airfoil shape, okay? I guess to be clear, what you're looking at is an airfoil. Airfoil is basically the cross-sectional or a slice of the wing, okay? So the wing, you can think about the wing, either the bird wing or the aircraft wing, protruding out of the page as you're looking at it. And if you take a slice of that wing, this is what the interior structure might look like. So we did some optimization, modeling, simulation, and optimization. We don't need to talk about this now, but that led to some prototypes. So this is one of them. This is where we developed, again, an airfoil, a slice of a wing, using two different types of piezoelectric materials that are on top of each other. And we put this 4-bar mechanism to give it the right motion. And then that led into this prototype that you can see here. So you can see that that the motion of the wing or the airfoil is, in fact, looks like a bird's tail, perhaps, except that there's still some mechanisms here that are still not very desirable. So there's still some there's benefits and some simplification because we used smart materials, but there are still mechanical components that are not desirable. So we went on to trying to eliminate those mechanical complexities, hinges, etc., etc. So we did some additional modeling and simulation and optimization. We come up with this structure. And then also we come up with other structures. So this one is another airfoil that we optimized for a different type of conditions. So in this case, you see the airfoil doing some sort of a breathing type motion. So this actually led to us thinking about a pump using this structure, okay? Right. So from those research, which is just a section of the wing, which is what we call an airfoil, we thought about trying to uh, look at the entire wing, and in fact, not only use the wing not only to produce lift, but to produce lift and thrust at the same time. So this is what birds do. So when the birds achieve flight by using their wings, just as fixed-wing aircraft do, to generate lift, if they have forward velocity, okay, or if they have any kind of a velocity, but also to provide that forward velocity, they of course they have to overcome the drag force, so they need propulsion. In a fixed-wing aircraft, the propulsion is achieved by the propeller, which is either the jet engine or the propeller that you see mounted on the wings or in front of the nose of the vehicle, depending on the aircraft that you have. Birds achieve this by simultaneously using their wings to flap in different orientations to achieve not only lift but also thrust at the same time, right? So they can produce propulsion and they can use their wings to generate lift and also to do maneuvers. So we wanted to be inspired by this mechanism, and so we wanted to make a drone or an aircraft with flapping wings, and these types of devices or systems are called ornithopters. So we looked at actually the wing of a preserved wing of a great blue heron. We did, again, dynamic modeling of the wing. We looked at different motions that it generates at different frequency of excitation. We then took carbon fiber. We manufactured a wing mimicking what the bird wing looks like, the great blue heron wing looks like. We added these smart materials or piezoelectric materials on the wing to make the wing flap, pitch, and heave. Um, and then we developed a test apparatus to kind of be able to test this wing. So now that you see that using these piezoelectric materials just adhered on the surface of the composite, we see that the wing is flapping just like a bird, okay? So this is still far away from generating thrust, but we're basically making progress towards that goal at this point. So in parallel or soon after, I also started taking this idea of moving the wings of a bird-like drone into basically the blades or the wings, so to speak, of a propeller. And this actually is what ties into the drone research. So the idea here is that, as I mentioned earlier in my presentation, in the first presentation, the major problem with drones is the noise that they generate. And of course, that's the major problem with helicopters, aircraft, and this is the reason why operating a helicopter in your driveway or a helicopter-like device in your driveway or an airplane-like transportation system in an urban environment currently is just unimaginable. It's just not practical and it will not be accepted. So the problem is that the common propulsion system, which works by taking a wing and simply rotating it in place, this generates a lot of disturbance to the flow, which is necessary to provide the propulsion. However, it creates this fluctuating flow, which then yields large levels of noise, acoustic emission, and this is what becomes unacceptable in many urban conditions. So we thought that we can actually change the shape of the blades to make them more quiet, or actually to change the shape of the blades to make them more functional without having the mechanical complexity that are required for these propellers. So we proposed this idea. We said that we're going to put these smart materials on the blades, so here, and we would put all of the electronics actually on the rotating system. And we don't want to connect any wires to the rotating system, so we do actually have a generator on the rotor, on the propeller, and it actually regenerates a little bit of energy from a magnetic field. So we have actually a drive motor, drive shaft, we have the propeller, and on the propeller or on the rotor itself, we have a generator to regenerate a little bit of energy to power all these electronics and the smart materials. So we successfully developed this idea. We built a prototype. We showed that it is operational. And we took that idea and then actually built a small quadcopter or a drone. We implemented the idea onto the 4 rotors, and we flew this aircraft. We've done some different prototypes of the same rotor concept. So this is another one that you see here. You're looking at the propeller from the top. It's actually on a bench stand to measure thrust force. So I'll show you a quick video what the operation looks like. Okay, so let me pull this into the screen. Okay. So this is actually a test where we're running a strobe light and a strobe frequency. So it's basically a flashing light onto the propeller. It's spinning so fast that with naked eye you can't see it, but with the strobe light, it's synchronized to the frequency of the rotor. So it creates almost like a static image of the rotor. So what you can see is an image of the propeller rotating in rotation. But then the piezoelectric materials are here that you see them. And it's actually, the shape is relatively flat because they're not actuated. So in a little bit later, what I do is I actuate it. I turn them on. And then you might be able to see. Okay, so it's the same propeller, except we applied electricity to this piezoelectric material. Now this plate is actually curved. So when it was flat, it was producing very little thrust or propulsion. When it's curved, now it's producing a lot of thrust. Okay, so the advantage of doing this is that we can actually directly change the shape of the propeller on the rotor without mechanisms, without motors, etc., etc. And we can do it. We can do this very fast. So now that, because we can do this very fast, we can actually do acoustic control to limit acoustic emission. Which, you know, normally you hear this sound, and this is actually quite annoying, of course. When it's a large propeller, this is actually much worse. So that's one of the prototypes that we built, and my students here, I advised a senior design project last academic year. So they kind of have continued on this research, and they've developed this structure or the test stand, which now is kind of a helicopter-like system. So we wanted to demonstrate this on a helicopter type system. So we took a commercially available small helicopter, or a toy helicopter basically. We put it on a fulcrum or a hinge to restrain its motion to just this vertical direction, to this vertical direction. And they built the prototype. We built the blades on it. And so here are the piezoelectric blades. Here's the conventional mechanisms that comes with a helicopter. Here's what the hinge is. So this vehicle would actually go up and down. This is where the electronics are, and then this is the controller, and the background is just my basically home office because this was in April, so I was doing experiments at home. Let's see. Okay, so I wanted to show you a video of this. Okay. Okay, so here's just a basic operation of a helicopter. Some of you might be familiar with this. This is called this is called a swashplate here. The swashplate here. So it's operating, of course, it's free to move up and down. So what we're going to do is we're going to turn on the propeller. It's going to start rotating, which shows its basic operation. And what I'll do is there's a segment of a video where I'm actually controlling the piezoelectric material. So you might be able to see from this little bit of shadow here that it's actually what I'm doing here in the control is that I'm actuating these piezoelectric material this shape, and that's what's causing the blade to move up and down. So I'll try to, yeah. So as I'm moving this knob, I'm actually sending a wireless signal to these electronics that sits here. The signal from those electronics are going through a wire that is inside of the shaft, and those wires are connected to the blades with the piezoelectric materials. Those piezoelectric materials are changing curvature, and that change in curvature is increasing and decreasing the thrust. That's why you're seeing the entire structure moving up and down, because there's more thrust is being produced. Okay, so that completes my presentations, two of them. So thank you for attending, and any questions that you have, I would be very happy to take them. And I'm just want to post or display my email and also the website. Okay. So if you want to see some of those research videos on your own, you can go to my website, and this will take you to my YouTube page. And on the YouTube page, there are many videos. If you have questions for later, or if you want to contact me, you can use my email. But otherwise, I'll just take the questions from Dr. Coutinho now. Thank you.
Fantastic, Honor. Really, really exciting to hear about all these developments. So there have been a lot of questions going through the chat. So I have put it in some order and paraphrasing some of the questions. So first, a question about the drone port. So, and the question is that what is the vision for the port? And whether it's only focusing on delivering medical emergency supplies, or is more broad, or is broader, including human transport and so on. And in a kind of related question is how these will differ from a helicopter port.
Okay, that's a very good question. So the intention of the drone port at the beginning has to be, I guess, multiple prongs, so to speak. So at this point, there won't be enough demand for transportation. In fact, there's no demand for transportation for drone operations. So at the beginning, the drone port, not in Manhattan, of course, in Rutgers airspace, would give you dominantly an area or a safe place to do research, and then to conduct testing, and then to have the industry, academia, and government to collaborate with each other to come up with systems that can actually enable drone operation along with current uses of the national airspace. So that would be the first intention. However, a facility this large, you want to have a long-term vision. And so the idea is that it's designed to actually to then be transformed into an airport or to kind of model as a heliport. You want to call it a heliport, an airport, or a drone port. We just thought that it would be appropriate to call it drone port because it would accommodate um, both unmanned systems and also manned systems, fully autonomous systems or individually controlled or manually controlled systems. And also the difference between I guess, a fundamental difference between an airport and a drone port would be that we think of airports as places where large vehicles take off and land with long runways. And these basically fundamentally cannot be in urban environments. Whereas the idea of a drone port that uses basically vertical takeoff and landing vehicles that look like helicopters, basically, that has the ability to take off in a vertical direction, the drone port actually would accommodate or would be designed specifically for such vehicles. And therefore, they can be placed in urban environments, and they would be no different than a bus station or a railroad station, that they would reach into the urban environment and provide immediate transportation. So yeah, that's kind of a short answer that I can provide.
Sure. I mean, and there are kind of a follow-up questions in that regard. I mean, one is what is exactly a drone? So is it small, big, or both of them, and so on? And so you mentioned the idea that this drone port probably is for a smaller vehicle. So one of the questions that we have is what exactly is the drone that you are thinking of, and what is your prediction for the future of the drones in terms of size and applications?
Okay. So just kind of a brief history on the term. So the drone actually refers to a bee, a male bee, and so this is the origination of the term. And in around when the first aviation or powered aviation started in early 1900s, so in around the 1920, 1930s, there were aircraft that were being used as target practice for manned aircraft. And these aircraft were making a buzzing sound or a humming sound. And they basically sounded like bees from a distance. So the kind of the nickname in the U.S. military was, or actually in also some other militaries as well, was that they were called a drone. So the drone historically referred to vehicles, whether large vehicles or small vehicles, but they were unmanned vehicles because originally they were used as target practice for either ground-to-air targeting or air-to-air targeting. So then, decades passed. Of course, they were continued to be used pretty much in the military, and they were mostly unmanned aircraft that could fly for very long periods of time at very high altitudes for reconnaissance purposes, etc. And then that technology kind of trickled down into the hobby aircraft. And then recently, in 2016, 2017, then the markets were flooded with toys, what we call drones today. So the term really refers to, it could be referred to as small autonomous aircraft, okay, or small autonomous aircraft. But in fact, many industries or many people would also refer to large autonomous aircraft drones as well. So the public may think of them as small vehicles today, but actually large vehicles are also called drones. And in the future, who knows? I mean, the term aircraft might become obsolete, and then all flying things might be called drones. So we're just referring, using the term drone to refer to aircraft in general.
So, I mean, kind of related, do you think that the drone port can also help better answer what are the regulation issues for the FAA. One of the questions is related what are the safety issues related with drones, especially operating in large cities?
Absolutely. So the issues, I think, the issues are, let's say, in two categories. One major category of issue is the policy and acceptance, and the lack of regulation. And the regulation or the policies cannot come in place when the technology is not matured. So you need a safe environment where you can develop drones, but not only develop, you can also use as intended in the future. So you need a large facility, and in fact, you need maybe multiple large facilities where these flights, let's say air taxis or air travel, personal air vehicles, can actually fly in between for pilot purposes or for testing purposes. So without these early demonstrations, then the public cannot have confidence in these technologies, and therefore policy will not be developed, and the restrictions will continue to occur. So a facility like DronePort is really enables that type of testing and to give people, the public, and the policymakers confidence that this is indeed possible.
So we have a few kind of technical questions. One is, what do you think is the practical payload before drones become mechanically inefficient? So
this is a very hard question to answer, but we can categorize them. So of course, you might consider a blimp a type of aircraft, and that might be considered a drone if you do it unmanned. So in that case, you can lift a large amount of payload with very little penalty, and with very little penalty on efficiency. However, if we talk about the small drones, the multi-rotor, quadcopter, or helicopter type drones, and if we say that they are battery operated, which makes them very convenient to use, very easy to, very low cost, easy to maintain, etc. They have very little flight time just on their own. Any added payload would make them actually very quite inefficient. So a good quality, high quality consumer type, but high quality drone, battery operated drone, a multi-rotor vehicle may have a flight time of 30 minutes with built-in electronics, camera systems, recording devices, etc. Any additional payload would just significantly reduce that flight time. So the point is that drones or any flying aircraft can become inefficient if you don't use it the right way, right? So a fixed-wing aircraft can be very efficient to go long distances. A lighter than air system like a blimp could also travel very long distances, or could lift very high payloads for long periods of time efficiently. And multi-rotor vehicles or vertical takeoff vehicles like these small drones can travel in short distances and do very basic tasks without lifting too much payload also efficiently. So it really depends on using the right vehicle or the right aircraft for the right task.
So here is a question related to these mega trends related to artificial intelligence and drones and so on. So, I think that more specifically, so how do you prevent drones from crashing into birds, or getting sensors that will be putting in and out of autopilot, and or whether linking to weather patterns and things like that. So, what are your thoughts on this area?
Yeah, so this is a really good question. So this is one of the technical challenges that is actually just recently a lot of progress has been made. So in my office, I have two drones. One of them is from DJI. I think it's about 4 or 5 years old in terms of the model year. Now that has very little obstacle avoidance. So it cannot see small tree branches. And just recently, actually, the beginning of this year, another company, so actually an American company called Skydio, come up with a model called Skydio 2. So that drone, within 3 or 4 years of additional development, is the same size. It flies that has roughly the same range and endurance, slightly less, but that can actually detect tree branches. So I can actually fly. I can tell this vehicle, this new Skydio 2, to track me visually, and then let's say do a loop around me or to do a circle around me. While it's doing circles, that circular path actually interferes with a tree or a wire. It will actually avoid that tree or avoid that wire as it's trying to do a circle around me. And it's doing all this calculation, the sensing, the imaging, image correlation, calculation of the path, obstacle avoidance, all within the computer that is embedded, or all of the AI embedded in the vehicle itself. So it's not only consuming power to hover and to fly, but it also has enough power to do this computation, to do this obstacle avoidance. So the technology is, in terms of AI, is moving incredibly fast. So I think this is an issue that will be solved. These kind of obstacle avoidance issues will be solved in 5-10 years. The noise is still a big problem.
Yeah, this is another of the questions, that the issue of noise, and there is a lot of questions about piezoelectric uses also for not just for these type of applications, but for other applications, and whether these things can be scaled to commercial aircraft and so on. So, any thoughts about that?
Yeah, so I'm working on a project where we're trying to scale this use of piezoelectric materials to an aircraft as large as possible. So we're looking at we're doing simulation, modeling and simulation of taking these things, piezoelectric materials, and scaling them up into transport aircraft in the size of 100 to 200 passengers or so. So we're doing some calculations. We saw that the deformations that we obtain become smaller and smaller. And so we're doing this research ongoing, and we haven't really come up with an answer yet, that whether it can be done or not done. So we're still in we're in the last year of this project. So we can see that we can obtain certain effects, and with the improvement of materials, or with better use of materials, we might actually achieve this. But the larger the aircraft, the stiffer the structures becomes, the more demand from the materials, and modern materials or current materials, they have their own limitations. So at this point, the commercially available products are best suited for smaller vehicles rather than larger vehicles.
So you mentioned before too the idea of taking decisions, or kind of capabilities, artificial intelligence capabilities that may be on the drone or maybe on edge computing or things like that. And there is also a critical part of these communications. How do you see the role of and 5G or 6G, this type of communications in the future of this linking drones with computing.
Absolutely, yeah. So, like rapid data communication is absolutely crucial for mobile applications. I mean, 5G, 10G, 20G, the larger, the better. So the problem is, in fact, the problem has little to do with drones or anything like that, but the problem really goes back down to the modern transistor technology. So the current transistors, since their first invention, the solid state transistors, since their first invention, have becoming smaller and smaller, have becoming also cheaper and cheaper. They follow this characteristics law, the Moore's law. Now the problem is that the transistors have become so small that the sizes are at the atomic scale. So with the current transistor technology can no longer become any smaller. So the only way to increase computational power to add more transistors. So this is why you have like parallel processors. This is why you have to use the cloud to do very complicated computations. So a mobile device or an aircraft, if it has to be a particular size, then it's going to have a fundamental limit with the current transistor technology, it's going to have a fundamental limit in how much computation that it can do. So a lot of the data has to be transferred elsewhere, and then the computation has to be done elsewhere, such as the cloud, where there are many processors available to speed up the computation time and then return valuable information back to the drone. So the role of 5G or increased bandwidth and increased speed in wireless communication is absolutely critical to both drones, aircraft, or all mobile technologies. And this is, of course, kind of I'm not thinking about a new leap or a new era in computational technology like quantum computing, etc., etc.
So we will do a couple of more questions, and we are reaching to the end of the allotted time. But if we, in any case, I will send all the questions that we have received to you, Onur, and perhaps if we have missed some, you can answer those questions by email.
Okay.
So one is, what is the expected range for these type of vehicles, right, that you have been describing?
The small vehicles, several miles. It really depends on the vehicle, of course, whether it's a multi-rotor vehicle or a fixed-wing air vehicle. Yeah, we're thinking about 5-10 miles. For fixed-wing aircraft, even longer distances. But for personal air vehicles or to do personal transportation, these have to be short distances, at least for now. So the main problem is really the battery technology or the energy storage technology. So with the current technology, the ranges are short and they will not become too practical. There are many examples of either companies or hobbyists trying to basically carry themselves up by making kind of oversized drones or multi-rotor vehicles. There's some really funny videos on the internet. I encourage you to watch them. But they just hover for a couple minutes and then they have to be brought down, just because the energy storage is, especially electrochemical energy storage, doesn't have enough density to carry a person for a very long period of time in the vertical thrust or vertical lift mode. So you can of course use gas-powered engines, but then it produces lots of noise, additional noise, and then they become very complicated because of the internal combustion engine. So they basically make the vehicle not very practical in urban environments. So you know, I talked about noise being a fundamental problem, policy and lack of data being another problem. But overall, of course, many technologies have a similar underlying problem is the source of energy and the energy density of electrochemical batteries or any type of a battery.
Well, I think with that, we will close this great talk. Thank you very much, Honor. Thank you, everybody, for participating. As I said, we are recording these. The school will make these available, and everybody will receive the information where it is available. Honor will get your questions if I haven't answered yet. And looking forward to the next talk. We have the chance to hear about all the great research that has been happening in the school. And so this time was Honor's turn. Thank you, Honor, and thank you, everybody.
Thank you for the opportunity. Thank you very much for attending, everybody.
Thank you, Kendra, for setting this up too.